Hello everybody, and welcome to lecture 3 of the 2D motion unit. And this whole lecture is going to be examples of solving various projectile motion problems. So my kids really enjoy The Legend of Zelda, and as many of you know, in The Legend of Zelda, the whole point of the game is to break as many pots as you can. So here's the hero Link, and he's really hit the jackpot, so to speak, this time. And he's throwing this pot off the roof of the Potter's Guild, and there's its initial velocity vector, and we're going to find these things. So before I start this, let me say that generally with a problem like this, there are many ways to solve it. So don't think that the way I'm going to do it is the only way. I'm going to go in order. There might be an easier way than going in the order indicated. And the first thing I had better do is define axes. So I've drawn myself some axes over here, and I am going to define up as positive for y and right as positive for x, and I am going to put my origin right where the pot starts. And that's a choice. I could have put it down here. I could really put it anywhere, but maybe the sensible places are down at the bottom of the building or right here where the pot starts. And I'm going to choose this one. So the next thing to do, just like when we were doing the one-dimensional UAM problems, is to write down all the things you know. But remember now, strategy, we've got two directions. We've got an x direction, and we've got a y direction. And they're separate, and they don't affect one another. So I really recommend that you divide your page and do everything to do with x on one side and everything to do with y on the other side. And now start writing down your knowns. So as before, we'll have an xi and an xf and a vxi and a vxf and an ax and a delta t, and we'll have all the same things for y. So I'm going to pause the video and I'm going to fill all of this in. All right, I've done the setup, and let's just check a few things over. So the initial velocity, you need to do a little bit of trig to get those two components, and I'm hoping that you know how to do that, and I've put a little bit of my trig here, and you should make sure you understand how I got those. Now, the kind of tricky thing here is that we're looking for the moment where it was going up before, and now it's about to be going down, right? The highest point. And so that means it's in the transition from going up to going down, and so our VYF is 0. That's one of the key realizations to be able to solve that. The other thing is AX is 0, and it's not really going to help us here, but that tells us that VXF is the same as VXI. So there we go. And I'll just mention that delta t is the thing that connects the two components. And so I've drawn a little arrow here to indicate that. And also I'm going to use 10 for g, and I've set up as positive for y, so my AY is negative 10 meters per second. So we're now ready to try and solve this. And as is usual with our strategy, we can just find whether we know four things. Remember, we're looking for YF. That's what we want, how high it goes. And so we know enough here. We know three things. We know A, VF, and VI, and so we can find delta Y, and that's going to be the third equation. So I'm going to write it out as we will use it. VYF squared equals VYI squared plus 2AY delta Y. And I'll solve for the delta Y. So delta Y is VYF squared minus VYI squared all over 2AY. And so now it's time to plug in some numbers and get a final answer. And I'll just notice you can make that a little simpler by realizing that that's 0. So I'm going to pause the video for a moment and plug in the numbers. So have a look. I simplified because I know VYF is 0, and so that's gone from the equation. And so when I plug in, I don't have to worry about it. So I have negative VYI squared over all of this. Notice that the negatives are going to cancel each other out, so I don't have to worry about any negatives. And also notice that we have seconds squared on top and bottom, so they're gone. And we have meters on the bottom and meters squared on the top. So we are going to get meters, which we'd better because this is a delta y. And my calculator informs me that this comes out to 1.3 meters. Now, watch it. That is yf minus yi is 1.3 meters. But of course, yi is just 0. So yf is 1.3 meters. It goes 1.3 meters up from where it started. And so, you might want to answer that at max height, it is 9.3 meters above the ground, right? Because it started 8 meters above the ground. And so if it goes up 1.3 meters, it's going to be 9.3 meters above the ground. So now let's do part B. And I've taken a moment to just clean a few things up to prepare for that. And in particular, we still are talking about the same initial moment. And so in the setup down here, I've left all of the initial information the same. However, notice that we are now relabeling what moment is f, right? Before, f was up at maximum height, but now f is down here as it hits the ground. So the first thing to do is realize that we have new things to fill in here. Some things have changed. And so let's figure them out. Now, here's where a lot of people have a really serious error that they make. And the reasoning is that when it hits the ground, its velocity will be 0. And so I see students all the time in a situation like this stick 0 in. Well, that's not correct, because remember, these equations, the UAM equations, only know about uniformly accelerated motion. So as long as this pod is flying through the air, it has this g down acceleration. At the moment it hits the ground, everything changes. Suddenly it has a very different acceleration. It's brought rapidly to rest, or maybe it bounces, who knows? In any case, the acceleration changes. The equations cannot see past that moment. And so if we're going to use them, we have to use values for just before the impact. So just before the impact, we know that Vxf will still be the same as Vxi because the Ax is 0. We don't know Vyf. However, what we do know is yf. The pot started at 0 in y. It ends up 8 meters below that, and we have set y as positive up. So our final value of y is -8 meters. So time to strategize. We ultimately want xf. But if you look at this, we're going to have some trouble. It kind of looks like we know 3 things and could find a 4th, but if you try, so let's say you're going to get delta x and you know both v's and a, and so it looks like you could use equation 3. Try it. If you plug it in, you're going to get 0 equals 0, which is certainly true, but not particularly helpful. So this is a no-starter. And so what we need is to find delta t, so we have another way of getting at it. Well, the y direction is what's going to give us delta t, because delta t is going to be found from finding out how long it takes it to get to the ground. So in that case, the easier thing to do, the direct way, is to say, oh look, we know delta y, we know vyi, we know a, we want delta t, and so that's equation 2. So let me write out equation 2 as we're going to use it. So we're going to say yf is yi plus vyi delta t plus a half ay delta t squared. Okay, and I can slightly simplify that because yi is 0. And if you look at that, you're going to realize that that's a quadratic. Okay, so I'm going to pause the video and I'm going to solve for delta t. you should try to do the same. Notice that I haven't plugged in any numbers yet. I've worked symbolically, and one of the biggest problems I see students having is that they plug the numbers in too early and they give themselves an enormous amount of work. Look, I can save myself a lot of effort by working symbolically and realizing that those are gone, that this gets squared so I don't have to worry about that negative, that this negative takes out that negative, that this 4 and this half result in a 2 here. And so now I'm ready to plug in the numbers. Okay, and so I'm going to have negative 5.1 meters per second plus or minus root 5.1 meters per second all squared plus, right, those negatives disappeared, 2 times negative 10, careful of the negatives that are inside the quantities, but then this yf is negative 8, okay, and so those negatives take each other out. So that's nice. All our negatives are gone. All divided by negative 10 meters per second squared. And at this point, you've got to plug that into a calculator. So be careful. We get 2 answers, and we'll have to discuss why we get 2 answers, but they are negative 0.85 seconds. Check the units, right? Meters per second squared. This is meters per second. This all comes out to meters per second. And so all that's left is a second. So we get negative 0.85 seconds or 1.87 seconds. Okay, and the plus gave us this minus value and the minus gave us this plus value. Let's talk about why. Why did that happen? Well, I mean, we're looking for an answer in the future. So clearly, our answer is this 1.87 seconds. But where the heck did this one come from? Remember that all we did was write down that this equals 0, and this is an equation for a parabola. Well, you know, equations are pretty dumb. They don't understand anything. And so this equation is obligingly saying, oh, you want to find when this parabola is 0, and there are 2 times, one here and one here, right? Well, of course, the pot was never here, it started here, but the equation doesn't know that. Okay, knowing that, it's now easy to finish this part. We just take that time. We now know enough to work in the x direction with this equation. A whole lot of things are 0, and we just plug our Vx and our time in, and we get our final x. Part C looks like it'll be a lot of work, but it turns out not to be at this point because of what we already know. One thing to notice is we already know one piece of the final velocity. There it is. Remember, we're talking about the same final as we were in part B, so everything here is the same. And so we're left just to find VYF, and that is going to be really easy because we can just say, well, VYF is, this is our first equation, VYI plus AY delta t, right? And so that's just going to be 5.1 meters per second plus negative 10 meters per second squared times our 1.87 seconds. I just took a moment to plug that into my calculator, and there's the answer. And we're actually done, because we can now just write VF vector is 14.1 meters per second I hat minus 13.6 meters per second j hat. And if you're objecting, what, don't I have to find a magnitude and direction? Well, if you're asked for a magnitude and direction, sure. But this is a perfectly valid way of writing a vector, and so there is our final answer.